Hey everybody, we're going to talk today about the Arrhenious equation, which is really the math behind the potential energy diagrams. So if we have a potential energy diagram, something like this, okay, we can actually calculate the activation energy, the energy over the hump, using this equation right here. Okay, now, there's a lot into this equation, and keep in mind that this E right here, that is the mathematical function E, not the not some sort of value or activation energy. So we know what K is. K is the rate constant, but A is the frequency factor. And we don't know what A is, and A is a constant that we would look up that varies dependent on the reactants that we're dealing with. And that has to do with the collision theory. And so if we're dealing with this in the collision theory, that's really what's going on. Remember that when a reaction happens, it happens because the molecules are colliding with each other for some, having the right amount of energy with the right orientation. And that's what A deals with. And then EA is the energy of activation. That's why it's E subscript A. And then R is the universal gas constant, but it's written in terms of energy, which is 8.314 joules per mole Kelvin. And then T is, capital T is obviously temperature. That frequency factor is kind of an interesting value. You can go to tables in books and look this up, but it would be really convenient, and we'll talk about this a little bit later, to be able to deal with the reaction without having to worry about the frequency factor, because that thing really kind of not fun to deal with. Okay, and so not only does it have to do with the frequency factor in terms of how often they collide with each other, but also with the correct orientation. So there's all sorts of things that go into this frequency factor, and that's why there are tables and tables and tables and tables and tables of A, of the frequency factor at different temperatures with different compounds and different elements. The other term deals with the amount of energy that the molecule needs in order for a reaction to take place. And notice that that value, R is a constant, is the universal gas constant, but notice that that value really changes based on temperature. And so that's kind of an interesting deal. The other thing that happens is that because it's a negative EA over RT in the power, as temperature increases, activation energy goes down. And that's what we see chemically speaking. And this is kind of the mathematical evidence for that. Now we can rearrange the equation. And when we rearrange the equation, get rid of the E, do stuff. And I'm not going to spend time showing you how to rearrange the equation. You get this. And like most equations in the kinetics unit, this is in the formula of y equals mx plus b, where this is our b, our x now is 1 over t, and ln of k is our y. That makes our slope negative EA over r. R is a constant, and so the slope of the line, we can figure out the slope of the line and get the activation energy fairly easily. I say fairly easily, provided that we have A and K and different temperature reactions. Okay, and so that's how we would do this. So you would plot and find the slope of this, and I think that that's the big key that I would like you to take from this video, is that anything that deals with kinetics, it seems like we can plot into this y equals mx plus b form and get useful information as long as we rearrange the equation. Okay, but that's not really what we do, because we don't want to deal with A at all. Okay, that's what we see here. If we take two equations and we subtract them, after we rearrange, and again, you have to trust me that, or you could go through and rearrange it. I'm not going to show you how to rearrange it here. But when you subtract them and you compare two different experiments, because you have two different experiments at two different temperatures, that means that you have two different rate constants. You can mathematically determine the activation energy fairly straightforwardly, because you know R, you know the rate constant. We've spent the whole unit dealing with rate constant, and T is just temperature. Remember, temperature is in Kelvin. Okay, that's important. Okay, and then R is just the universal gas constant in energy, 8.314 joules per mole Kelvin. And so that means that you can calculate activation energy fairly straightforwardly. And so I have a couple of examples here, and it says calculate the experimental, using this experimental data, calculate the activation energy. And so in this case, you would pick any two of the experiments, any two that you would want, and you would plug it into the equation that we just had, okay? Or that we were just using, the ln of K2 over K1 equals negative EA over R 1 over T2 minus 1 over T1. And you would plug that in, and I don't necessarily want to diminish the math that goes into it, but then it becomes a plug and chug sort of equation. And so when I plug this into my calculator, I get a final answer of 3.833 joules per mole reaction. Okay, and that seems pretty decent. 3.8 kilojoules is a fairly reasonable number to have as an activation energy. And so as you do this, your temperature is going to fluctuate up and down, but then the rate constant is going to reflect that temperature. So your activation energy will probably be the same for that reaction no matter what, whether the energy is coming from the collisions or whether it's coming from the temperature. Like that's the whole thing, is the activation energy is going to stay the same throughout. Now the next one is the same thing. You can, given these two values here at two different temperatures, you can again use the same equation to find the activation energy. And again, I'm not going to try to diminish the math, but I don't necessarily want to focus on the math. So I'm going to give you the answer. And when I give you that answer, it'll be 2636 joules per mole reaction. Okay, so that is another reasonable activation energy. It's probably 2.6 kilojoules is a little bit easier way to put it here, because it's kilojoules per mole. Kilojoules is kind of the standard energy thing. So that is the activation energy. And keep in mind, you're probably not going to have to calculate it, but I think that knowing how to plot it here, or not plotting it, but using this here, that you can rearrange it, is helpful. And so is this, where you can then just use the two different rate equations at two different temperatures. Like, the ideas of those are what is important here. So that's the Arrhenious equation, and enjoy.